thank you all for coming. Thank you for inviting me. So I'm going to be talking today about some work that I've been doing with collaborators at various institutions, most notably NICHD, where we adjusted for non-compliance in a randomized trial looking at the relationship between aspirin and pregnancy outcomes. So just some information. If you're on Twitter, you can follow me there. I have a GitHub page where you can watch how I ruin perfectly good code. And I have a website which I do intend on posting the slides to, so if you want to take a closer look at these slides in the next few days, I'll post them, and you're welcome to just download them there. Before I start, I want to acknowledge the collaborators in this work. So there's Enrique Schisterman, who is at the NICHD, who's the PI of the actual study that was done, the EAGER study that I'll be talking about today. As well as Sonny Mumford and Neil Perkins at NICHD, Steve Coles at UNC, and Robert Platt at McGill. So we've all been working on this, and the final result would not have been what it is without their input. Any and all mistakes that I may have made that you may catch in this slide, you can actually blame Steve Cole, because he was my PhD advisor and he should have trained me better. So I also want to thank Stella for putting this together. And Sue Bevan, who's at SER, for organizing the SER talks. And here's just an outline of what I'll be talking about. So really the study that was done was to examine pregnancy loss and how to mitigate pregnancy loss. So I'll talk a little bit about that, and then I'll jump right into the EAGER trial, the trial that was done. I'm going to be a little bit unconventional with how I order things. So when I talk about EAGER, I'm going to present some of the results that have already been published, notably the intent to treat results that were published in The Lancet in 2014. And then I'm going to talk about intent to treat. I'm going to sort of explain what it is and what it's not. And I'm going to argue that, in fact, intent to treat isn't sufficient as an indicator of the effect of exposure on an outcome. And I'm going to show you how it's affected by non-compliance in a trial. I'll introduce the per protocol effect and how we estimated that. And then my methods section is basically going to be a description of G-computation. So it's a little bit involved and, again, unconventional. So I will actually stop for questions if there are any during the course, anywhere during this presentation, particularly when I explain G-computation. I tried to frame it in a way that doesn't require any technical understanding. But again, if you do have questions, I'd be happy to answer them. And then I'll present the results that we got from this per protocol analysis, which I think are very exciting. So this talk is about pregnancy loss. So what is pregnancy loss? Well, it's actually the most common pregnancy complication in the United States. It occurs in roughly 20% of recognized pregnancies and 30% of conceptions. Among women who have had a pregnancy loss, they are likely to have another one, so roughly 20 to 30% recurrence rate. And there are several underlying etiologies for pregnancy loss, but for the most part, it is idiopathic. Roughly 50% of pregnancy loss in the United States is unexplained. So so the treatment options are also limited. For the most part, what's done is the use of assisted reproductive technologies, and they are successful. However, they're also very costly and potentially invasive at times. There's also the beginnings of some evidence suggesting that they may be associated with an increased risk of birth defects. So naturally, identifying safe and cost-effective strategies to reduce the risk of early pregnancy loss is a clinical and public health priority. Right, to understand what we might be able to do about pregnancy loss in the United States, a little context and background on the pathophysiology of pregnancy loss is warranted. So there are a number of underlying mechanisms that explain potentially why pregnancy loss occurs, and these include gynecological, endocrinological. Most notably among these, a lot of research is focusing right now on the immunological aspects of pregnancy loss. So pregnancy itself is a very complex immunological process, and the survival of a fetus depends largely on how the balance of pro-inflammatory and anti-inflammatory factors turns out in a given pregnancy. In fact, pregnancy itself induces some inflammation, and that is required in order for the conceived embryo to implant into the uterine wall, ultimately leading to a successful pregnancy. However, if the inflammation is uncontrolled or long-standing and persistent, the thought is that it leads to harm, loss of the fetus among them. So our working hypothesis was that uncontrolled and persistent inflammation is partly responsible for the large proportion of unexplained recurrent pregnancy loss in the United States. So given that inflammation may be a major underlying factor here, what are the options? Well, one option is to actually use anti-inflammatory drugs. For example, aspirin. So aspirin is a widely known over-the-counter drug. It's inexpensive, it's available widely, and it has been shown to have beneficial hemodynamic and immunomodulatory effects on reproductive organs in particular. There's also evidence that shows that it's fairly well tolerated, up to 150 milligram doses per day in pregnancy. Evidence exists that shows that aspirin consumption actually does reduce the risk of pregnancy loss in women with antiphospholipid antibody syndrome. So this is just a condition that as a high leads to a high risk for pregnancy loss. However, there is very little that's known about the benefits of aspirin in women who are having unexplained pregnancy losses. So what I'm showing you here is a Cochrane review that was done in 2014, and what they did was looked at the literature at how various anti-inflammatory drugs are associated with pregnancy loss. So this figure here is just showing you sort of the forest plot of all of the results available for aspirin and unexplained pregnancy loss. And what you can see is that there are not very many studies, and most of the effects here are basically very close to the null. So the authors of this Cochrane review found several problems with the available literature. Most notably, they all suffered from small sample sizes and insufficient power to detect important effects. Some of them had no placebo control. Many of them had an unconcealed treatment allocation, and there was baseline covariate or confounding, baseline covariate imbalance or confounding in a number of the trials. So the authors of this Cochrane review concluded that, quote, large randomized controlled trials assessing an effect of anticoagulants in women with recurrent miscarriage are urgently needed. And this is where the EAGER trial comes in. So the EAGER stands for the effects of aspirin on gestation and reproduction. EAGER was a multi-center, block randomized, double-blind placebo-controlled trial that recruited 1,228 women. Women were included in the trial if they were between 18 and 40 years of age, if they were actively trying to conceive, and they were randomized to 81 milligrams of aspirin per day or placebo, so that 81 milligrams is low-dose aspirin. All women received 400 micrograms of folic acid in addition. The study protocol consisted of study visits that occurred every 2 weeks for the first 2 months and then monthly thereafter, and follow-up ranged from between 1 and 80 weeks, with a total of 286,995 person days on study accrued. So for the purposes of this talk and the results that I'll be presenting, the time scale of our analysis will be the weekly time scale, so everything will be sort of explained in terms of weeks. In the trial, pregnancy was assessed using daily urine tests, self-administered urine tests, and was confirmed with ultrasound at 6 to 7 weeks of gestation. And then follow-up ended for each woman after either 6 cycles with no pregnancy, 6 menstrual cycles with no pregnancy, or with one of the study outcomes, pregnancy loss or live birth. So again, so this may be the unconventional part here. I'm actually showing you some of the results from the EAGER trial that were published in 2014. So here I'm just giving you a sense of what the EAGER trial looked like, what the sample of participants looked like. I won't come back to this issue until at the end of the talk when I discuss the limitations, but it's important to note As with most samples, most randomized controlled trials, there was some sample selection issues. So, 95% of the women in the trial were non-Hispanic white. Most of them were married. They were very well educated, employed, and had relatively high annual household incomes. So this is an issue that is often unaddressed, and actually the next step in the analysis that I'll present to you today, I don't have results on this, but the next step is to actually adjust for this particular kind of problem, this selection problem. What I'm presenting to you here are the results, the intent to treat results of the trial. So the LDA column here, this stands for low dose aspirin, and this is the number of women in that column, and this is the placebo group. And what Enrique found was basically there was a very small effect of aspirin assignment on live birth, but there was no effect of aspirin assignment on pregnancy loss, as you can see here. They did not present this in the trial, but I will be talking about the effect of aspirin on conception, and so it's easy to compute this effect using the data that we provide here. And you see results that are similar to the live birth results, a small effect of aspirin assignment on the conception rate in the trial. So these were the intent to treat results. What do they mean? Well, to understand what they mean, let's get into what the intent to treat effect is. So here, the intent to treat effect can be interpreted as the following contrast. So this is the risk of the outcome, for example, live birth, that would be observed if a woman was randomized to receive the treatment, minus the risk of the outcome that would be observed if a woman was randomized to placebo group, right? And the beauty with intent to treat or with randomized trials in general is that one can identify this effect using the sample average in the study. So this is just the average outcome among those who were actually received treatment minus the average outcome among those who received placebo. However, this measures the effect of treatment assignment and not the effect of treatment itself. And it's important to note that this effect, though not biased by noncompliance, so that is, if a woman was assigned to take treatment but she didn't actually take the treatment, it is not biased by noncompliance. However, the intent to treat effect depends on noncompliance. It will change in the presence, potentially change in the presence of noncompliance. So the intent to treat effect quantifies the population assignment effect under a very important condition, and that condition is that the sample of participants is actually representative of the population that we want to infer this effect to. Okay? So this includes the characteristics that I showed you in that table, but it also includes the sample rate of noncompliance and the dynamics of noncompliance that occurred over time. Right? So basically, in order to interpret these ITT effects as what we would see in the population, we have to assume that even after the study was published and shown to have some slight or moderate success, that women in the future will behave the same way that they did in the trial. So the group at NICHD anticipated this, and they designed the study in such a way so as to collect a lot of information that we could use to correct for any potential noncompliance that would be observed. And so in EAGER, compliance with the study protocol was measured several different ways, including prospective and retrospective self-report, bottle weight measurements that were taken at each study visit, as well as using urinary aspirin metabolites. And what I'm showing you here is the pattern of noncompliance in the trial. So this figure is basically documenting the entire course of follow-up, and the proportions that I'm showing you here are three. So the first, this dashed dotted line, represents the sample that remained on study. So as the study progressed, women were either censored or they had one of the terminating events and they ended up leaving the study. And then the dashed line here and the solid line here represent non-compliance. So this is the proportion of women who were compliant early in the study and later on in the study, as measured with bottle weight and with prospective and retrospective self-report. Right? So what you can see here is that at some point, relatively early on in the study, the compliance rate dropped to about 80%. So we wanted to know how much did this affect the results? And that's what we did. So we did this by quantifying the per protocol effect, which I've defined for you here. So this is basically the risk of the outcome that would be observed if all women, say, were assigned to treatment and they actually took treatment. That's the x equals 1, minus the risk of the outcome that will be observed if all women were assigned to placebo and they stuck to their placebo. Unfortunately, with the per protocol effect, we don't have that same connection with sample averages, right? So we can't simply estimate the per protocol effect by looking at the proportion of events among those who were assigned and who took treatment versus those who were assigned and didn't take treatment. And the reason is that the act of taking or not taking the treatment on a daily basis can be confounded by post-randomization confounders. So in order to estimate the per protocol effect, we actually have to adjust for any predictors of noncompliance, right, that may also be associated with the outcome under study. In the context of a point intervention, the trial of a point intervention, say for example a surgery or a drug that's taken only once and not again, adjusting for noncompliance is a relatively straightforward thing to do. However, when the intervention under study consists of a series of actions that occurs repeatedly over follow-up, such as taking aspirin on a daily basis over 500 days on study, adjusting for noncompliance can actually be a little bit more complicated. And I just want to point out that you might be familiar with various ways to adjust for noncompliance in a trial. One of those is to estimate what's called the complier average causal effect. That's not what we did here. We did something different. And so the per protocol effect and the complier average causal effect are two different quantities, and we sought to estimate the per protocol effect. So why do we have to adjust for predictors of noncompliance? Well, so consider the following diagram. So what I'm showing you here is just a representation where X represents whether or not a person complied at a given time, J. So you can think of J as a day, and J plus 1 will be the next day. Taking aspirin on day J might result in some consequence. For example, gastrointestinal discomfort, right? That gastrointestinal discomfort may result in that woman not taking aspirin the following day, right? As it turns out, in the EAGER trial, there's actually a paper that showed an association between GI discomfort and the outcomes under study, right? So there's reason to suspect here that time-varying confounding affected by prior exposure is present, right? And in the presence of such confounding, one cannot use standard or typical methods to adjust for the confounding. So, it is an unmeasured confounding, yes. So, for example, if we use standard regression, that would be equivalent to basically conditioning on this variable, this gastrointestinal discomfort variable. And in doing so, we end up actually blocking a large part of the effect of interest that we want to quantify here, right? The other thing that we do when we adjust for Z is if there are any unmeasured confounders here of the relationship between gastrointestinal discomfort and the outcome under study, we induce what's called a collider stratification bias. So it opens up this association, which is not an association that we want to be quantifying in our study. Right? So that's the problem with using standard methods in the presence of variables that are measured repeatedly over time. Okay? And this is actually a major problem with a lot of the literature that seeks to adjust for noncompliance in trials. So in trials, the per protocol effect is most commonly estimated using a number of different strategies, all of which are rather ad hoc and which are not guaranteed to work. So for example, when a trial is conducted with a complex intervention, oftentimes researchers will summarize a very long history of compliance into a single number. So for example, they'll take the average compliance for a given individual, and then they'll say that that person will be deemed a complier if that average is above, say, 80%. Right? And then the next thing that they do is they'll often look at the risk among the compliers and non-compliers without adjusting for any predictors. If they do adjust for those predictors of compliance, they typically tend to use standard logistic regression to do that. Each of these techniques can lead to considerable bias in the estimation of the per protocol effect. So what we want, ideally, is to use a method that can do two things. One, that can accommodate variation in compliance over time. So what I mean by that is that we're not forced to take this very long history of compliance for a given individual and cram it into a single number. Actually, we want a method that we can use to sort of tease out the effects over time, right? The other thing is that we want a method that will correctly adjust for time-varying confounding, for the time-varying confounding that is present potentially present in a trial. And G-computation is a method that can do that, right? So now I'm going to get into my methods section, okay? So again, this might seem unconventional, so feel free to stop me if there are any questions. What is G-computation? So G-computation is actually, it's also known as the G-formula. You may have heard of it as the parametric G-formula. These are all the same, G-computation, G-formula. And essentially what it is, it's a generalization of direct standardization to the setting where the exposure and the confounders are measured repeatedly over time. So if you know how to standardize, you really do know what G-computation is, right? I just want to clarify, this is an issue that comes up repeatedly everywhere that I go. There are a number of different G methods, and G-computation is not the same as G-estimation. G-estimation, turns out, is an instrumental variable-based approach, whereas G-computation is a more general standardized type approach. So in the next series of slides, what I'm going to do is I'm basically going to tell you exactly how we implemented G-computation in our sample, right? So I'm going to do this in two ways. The first way is I'm just actually going to say it. And then after I tell you, I have a series of slides that sort of walk you through the G-computation algorithm. It's sort of like a flow chart. Hopefully that'll convey some of the intuition behind what's happening. But we'll start with this here. So what we did was, first we actually split our sample into the randomized group and the placebo group. So everything that we did separately in these two groups in order to better accommodate potential differences in for example, interactions between randomization and all of the confounders and covariates that we had in our study. So in each randomization stratum, what we did was we fit regression models to all of the relevant variables, and those relevant variables were ordered causally, right? So we assumed that in terms of how things unfolded in our study, that live birth was the last, so at any given time point, live birth was the last variable in the causal order. And before live birth came pregnancy loss. Before pregnancy loss came this end of follow-up without pregnancy. Before the outcomes came conception, right? So an indicator of whether at a given time a woman conceived or not. Before conception came compliance status, and then we had our time-varying confounders, which included bleeding and nausea at every given time. And then we also had a whole lot of time-fixed confounders. So these were baseline confounders whose values didn't change as follow-up progressed, and I've sort of listed them here. And so in terms of the modeling, basically the modeling just consisted of standard regression models, right? So we fit a logistic model for live birth, and we regressed that against everything that came before it. We fit a logistic model for conception and regressed that. At each time point, we regressed that against everything that came before it, right? All of the variables that we entered in these models, if they were continuous, we entered them using natural cubic splines with either between 2 to 5 degrees of freedom. And all of the categorical variables, we used dummy coding to enter these variables in. Okay, so now what have we done? So now we have a series of regression models fit to our data, right? So you can imagine each regression model, we took its information and we stored it in our software program somewhere else to the side. So we had all of these stored models. The next thing that we did was we resampled our original sample of 1,228 women. We resampled the first time point for each woman as well as all of their time-fixed covariates. Okay? And we did this 25,000 times for each randomization stratum. Right? So in the randomized group, we took the baseline information from each woman 25,000 times. We upsampled them, right? And we did this in order to quantify the per protocol effect using what's called the Monte Carlo algorithm, or the Monte Carlo estimator. So that's this MC. Our Monte Carlo sample was 50,000 observations. So now we have our models fit that we've stored to the side, and we have this resampled baseline data. And what we did was we combined each of those, and we used the models and the baseline information to simulate follow-up for the entire sample. Okay? So that's all we do in the G formula, right? But I know that that's not very intuitive, so I'm going to walk you through it again with this sort of illustration. So imagine that we just resample one woman. So let's say we have information on one woman, and at the first time point, that information is represented by everything in this box here. So here the V's represent all of the baseline covariates. So we had roughly 20 of those V's there. R represents the randomization indicator. Say this sampled woman had an R value of 1, right? XM represents the compliance status for the first week. Did she comply? Did she not comply? So here M is equal to 1, and that's the first week. BM represents the bleeding status in the first week. ZM represents whether the woman had conceived in the first week or not. And by definition, in the first week, none of the events had occurred, so there is no censoring, there was no pregnancy loss, there was no live birth, so we don't need to include that. It's all 0. We don't need to include that here. So what we did with this information was we took the model for compliance that we fit, and we used that model to predict whether compliance would have occurred at week 2. Right? So we advanced the time by 1, so now we're in week 2, and we use this model and this baseline information to predict, does compliance occur? Once we predict compliance, we do it again for bleeding. Okay, so we use the predicted compliance value and all of this baseline information to predict whether bleeding occurs, right? So now we've predicted bleeding, so now we have 2 simulated variables. One is the compliance at time 2 and one is the bleeding at time 2. Then we ask the question, in the previous time point, did a conception occur? And if a conception occurred, then we'll set the conception variable to 1 in this time point. Why? Because in our study, conception was what's called an absorbing state, meaning once a woman conceived, when conception ended, she was out of the study by definition, right? So we were able to just do this. If she did not conceive, well, we'll use the model that we fit for conception and predict whether she conceives in this simulated setup. Again, the model is regressing, it was predicting based on all of the previous predictions and the baseline information. Okay, so how are we doing so far? Is this okay? Okay. So the next question that we ask is, we draw from that model for censoring. Right? So there were some women who were censored. We want to account for censoring in our study, so we had to model it. So we draw from the model for censoring. And then we ask, was this woman censored? If the woman was censored, well, that's the end of the follow-up for her. Otherwise, we can ask another question. So these arrows here, so this is basically just saying that if the woman did conceive, then we're going to shift her to the red side. But if we happen to have predicted a value where she didn't conceive, we're going to stay on the blue side. So it'll make sense as we progress here. So for those women who didn't conceive, after we've predicted their censoring and shown that they weren't censored, the next question we ask is we draw from the model for end of follow-up without pregnancy. Would this woman have ended follow-up without pregnancy? If yes, well, that's the end. If no, well, then what we do is we go back to the beginning, we advance the clock by 1, and we repeat the whole process again, right? If the woman did conceive and wasn't censored, we continue with this process. We ask, was there a pregnancy loss? If there was a pregnancy loss, well, that's the end of follow-up. If there wasn't a pregnancy loss, we draw from the model for live birth and we ask, was there a live birth? If there was, end of follow-up. If there wasn't, and if the week on study is less than 80, well, then we go back to the beginning, we advance the week on study by 1, and basically continue this process until each of the 50,000 observations that we resampled has one of these events that terminates follow-up. How was that? Was that okay? That's the G-computation algorithm right there. Okay? So what I just described to you is an algorithm that will allow us to recreate the sample, really, because I haven't changed anything here, right? So I'm just basically simulating what was actually observed in the sample. But if I wanted to go and now estimate effects, I have to do something. And what we do is we go into our algorithm, and for everybody, irrespective of what their value was, we set R is equal to 0, and we set their compliance equal to 0, and we set all of their compliance values equal to 0, and we want to adjust for censoring, so we actually prevent anyone from being censored in our study, in this simulated study, right? And then we implement this algorithm. And as it turns out, the algorithm will now yield events like pregnancy loss and live birth that would have been observed had we intervened and set everybody to take placebo, right? So what did we do? So here's what we did. So the first thing that we did is we estimated what's called the natural course. Right? So this is just running the algorithm without changing anything. And we do this as a check. We want to sort of ensure that the simulated follow-up looks as close as possible to the actual follow-up. Right? If there's a very big difference between the simulated follow-up and the actual follow-up, then that tells us something's not right, because we're supposed to be getting what we observed in the actual trial. So that's the first thing that we did, was we implemented the natural course. In a randomized trial, you can actually use the G formula to do another check, which we're calling the G-ITT effect, right? And what we do here is the only thing we do is we first change randomization indicator equals to 1 for everybody. And then we go and run the algorithm and get all the outcomes. And then we go back and switch the randomization indicator equals to 0 for everybody and run it and get all the outcomes. And that allows us to basically estimate the intent to treat effect. So this is another check that allows us to see, are we able to capture the intent to treat effect that was originally estimated in the trial? So these two steps are our model checking steps. Once we run these model checks and everything's working the way we expect, we then start to estimate things, right? So for the per protocol effect, all we have to do is go in and set everybody's randomization indicator equal to 1 and set everybody's compliance equal to 1, run the algorithm, get our outcomes, store them on the side, and that's that. We then do the same thing for randomization and compliance equals to 0. So now we have these two simulated data sets with outcomes under two different scenarios. We can summarize those outcomes using, for example, risk measures, and we take the difference in the ratio of those risks. We get risk ratios and risk differences. We also did a third analysis, so one question that has not been answered in the literature is whether it's important to take aspirin before conception occurs or whether it's important to take aspirin after conception occurs, and how much of the unimportance is it, right? So what we did was we ran this per protocol by conception status, which is we set randomization equals to 1, and we set the compliance status equals to 1 only if the woman had conceived. Otherwise, compliance was 0. So this corresponds to the rule, only take aspirin once you've conceived. Otherwise, don't take aspirin. We also did the opposite, which was to set compliance and randomization to 1 only in the absence of conception. So this corresponds to the rule, once you conceive, stop taking aspirin. So our results. So the first thing that I'm going to present to you are the results for the G-ITT analysis, right? So here I'm showing you the same results that I already showed you, the intent to treat results in the original trial. And as it turns out, when we run our G-computation algorithm, we get the same thing. So there's no major difference between the intent to treat result that we estimated using the G-computation algorithm and the actual intent to treat results that were estimated in the trial. So this is telling us, okay, things are looking okay, like the way they should. We expect to see this. So in the next series of slides, I'm going to present to you results using this figure. So it's a little bit unconventional, so I'm going to talk to you about what it is. So here, I'm showing you the cumulative proportion of these two events overlaid one on top of the other, right? So over here, this is the cumulative proportion of pregnancy loss. And over here, this is the cumulative proportion of pregnancy loss and live birth. And I've divided the events into this much. So basically, what you see here, this is the proportion of live birth events that occurred, and right here is the proportion of pregnancy loss events that occurred. And at the end of follow-up, this proportion is equal to the number of conceptions, so the proportion of conceptions in the trial. Okay? So if you're familiar with survival curves, I take 1 minus the survival curves, and then I combine the two survival curves for the events of interest here. Okay? So this is what we actually observed under the natural course. This is sort of like trying to reproduce the trial, right? And we compared that to the actual cumulative distribution functions in the trial, and what we're seeing is, for the most part, we have a pretty close match for both pregnancy loss and live birth. So the green lines that I'm representing here are just from the bootstrap. I resampled using the bootstrap and fit these empirical cumulative distribution functions over and over again, right? So again, now we have another indication that tells us, well, we're doing pretty good with our algorithms. Our G-computation algorithm is able to reproduce what we expect it to. Okay, so now I'm going to present results. Here's what we would observe if everybody were unexposed in the trial. So notice what happens. The overall proportion of conceptions goes down. The role of pregnancy loss is much more prominent, and the live birth proportion goes down as well. Okay, so now let's ask, what happens if we intervene and everybody takes the exposure? Okay, so the conception rate goes up, and pregnancy loss rate goes down quite a bit. Okay? So now we can ask, well, what happens if we tell people, I can't remember which one comes first. What happens if we tell people to take aspirin only prior to conception? Hopefully that's the one that we'll see. Yes. So what happens if we take aspirin only prior to conception, but then once you conceive, stop taking aspirin? So the conception rate is still high. However, roughly half of all of those conceptions end in a pregnancy loss. Right? What about if we tell women only take aspirin once you've conceived? The conception rate goes down, but most of them are live births. The pregnancy loss rate is also very low. Okay? So those are the results presented in sort of absolute terms, and what I'm doing here is I'm just presenting contrasts in those results, in those figures that you saw. So here we have the proportion of conceptions among, under the regime, don't take aspirin, the proportion of conceptions under the regime, take aspirin throughout the entire course of follow-up, take aspirin only prior to conception, and take aspirin only following conception. So these are the proportions, or sort of the risks. And here I'm taking the contrasts. Throughout, I'm using the unexposed as the referent group, right? And so I'm giving you risk ratios and risk differences. So let's just focus on the risk differences. So this is telling us that for every 100 women in the study, if they were to take aspirin throughout the entire course of follow-up, there would be 24 more conceptions relative to if they didn't take aspirin at all, right? So same thing for if they took aspirin prior to conception. Okay. Here is the same corresponding results for the live birth outcome. So for every 100 live births, if they were to take aspirin throughout the entire course of follow-up, we would see 40 more live births relative to if they wouldn't take aspirin. And what's interesting here is that this is split roughly half and half between the two interaction regimes, right? So take aspirin before conception versus take aspirin after conception. And for pregnancy loss, 15 would be prevented for every 100 women in the study. And all of it is happening as a result of post-conception aspirin. Okay? So basically, the interpretation is as follows. Aspirin has a very large effect on conception, a large per protocol effect on conception. Aspirin has a large per protocol effect on live birth, and it has a very negative per protocol effect on pregnancy loss. Furthermore, the per protocol effect of aspirin on live birth is equally shared by pre and post-conception exposure. However, the per protocol effect of aspirin on pregnancy loss is due entirely to post-conception exposure. So that's basically what I had to show you today. Before we finish, it's important to talk about some issues and some limitations, right? So the first is, as I noted, we have a very restrictive sample, right? So in fact, the generalizability of our per protocol results is also very limited. And we are currently doing work right now to transport the per protocol effect to populations that are more representative of US women trying to get pregnant. So that's what we're doing now. But we have a good start in that we are showing pretty substantial per protocol effects. The other thing to consider, and it's another thing that we're currently addressing, is in the figure where I showed you the proportion of compliance measured via self-report versus via bottle weight, we saw some differences in those proportions, which suggests that there may be some measurement error in terms of in the way we measured noncompliance. All of the results that I presented to you were based on the bottle weight measurements of noncompliance, which we believe are more objective than the self-report measures. However, we're currently developing techniques to correct for potential measurement error using some form of triangulation between our self-reported measures, our bottle weight measures, and the aspirin metabolite measurements that we have. And so these are two up-and-coming projects that we've started working on. The other thing that we have to consider is anytime we do an analysis like this is we actually, in order to interpret these things as effects that would be observed if we were to intervene and have everybody take aspirin versus not, is that we need assumptions to do this. And these assumptions are fairly well known in the causal inference literature, three of which that I'm not too worried about include the consistency assumption, the interference assumption, and the positivity assumption. In fact, the positivity assumption is verifiable. We can check the status of this assumption, and our checking told us that there really is nothing to worry about there for positivity. However, we also have to make additional assumptions, and these ones might present more of a concern here, notably the exchangeability assumption. So what this implies is that we've measured all of the important confounding variables, time-varying confounding variables. I mean, I can tell you that we don't believe there to be any other variables that are of great importance here, but again, that's me saying that there really isn't, so there could always be something that I'm missing. One main limitation of the G-computation algorithm is that we have to model all of these variables, right? Which means that we have to correctly model all of these variables. So any misspecification in these models could potentially lead to bias, right? And it's impossible to determine whether you've correctly specified these parametric models. So this is, again, another unverifiable assumption. We also have to assume that when we ordered the variables causally, we did this correctly. Again, an unverifiable assumption. However, when we redid the analyses using different orderings, nothing really changed. So we're sort of confident that the ordering, if it's wrong, it doesn't matter.
Do you have to make the parametric assumption?
Yes. There's an easy answer and a more complex answer, but the easy answer is yes. If you use non-parametric techniques, you open up another can of worms.
Right.
Yeah.
And probably your sample size is not.
Yeah, but it's related to sample size concerns, but there's a whole other thing that comes into play. So incidentally, though, we also did this using random forests and found results that were very close too, but don't want to advertise those too loudly. Okay. Okay, and that's all I had. So in conclusion, aspirin is important.